Hello folks, so in this video we are going to talk about hypothesis tests for the difference between proportions. So just like one proportion tests, we are going to use hypothesis tests to determine if an observed difference between proportions reflects an actual difference in our parameters, okay, or if it's due just to chance variation, right? So a lot of the processes you're going to see here are going to be the same as your one proportion tests, right? It's just because, again, we're dealing with two populations that you often will have have to pull double duty, and your hypotheses change a little bit. The standard deviation equation changes a little bit. So here are the changes that occur, okay, between one and two proportion tests, okay? So your null hypothesis, okay, is that there is no difference between the parameters, okay? Right, i.e. your population proportions. Okay, that's the null. We're assuming no difference or no change, right? There are two ways that you can write that, okay? You can either write that, or you'll see it written as P1 minus P2 equals 0, okay? Or you will see it written as P1 equals P2. Okay, those are the two ways that you might see it written. I'm going to recommend, oh, that was terribly drawn by me. Let's just go with this one. I'm going to recommend that you write it the first way. Okay, and you'll see why when you have to plug stuff in to the test statistic, right? If you write it this way, you will have an actual value for the mean, right? Or the parameter value, right? And that value is 0, all right? Now, for your alternative hypothesis, okay, there's 3 different types, very similar to what we did with one proportion tests. Okay, either that there is a difference, right? So that difference is either greater than, less than, or not equal to 0. Okay, so either one population is greater than the other, less than the other, or simply that the two are different. Okay, and again, there are 2 ways that you can write these. Okay, so for your greater than hypotheses, right? That's P1. You can either write it as P1 minus P2 is greater than 0, or you can write it as, oh, hold on, folks. Some weirdness going on here. Okay, or you can write it as P1 is greater than P2. Okay, and then you have a similar way that you can write these for less than, where P1 minus P2 is less than 0, or P1 is less than P2. Okay, and then again, same idea for not equal to. One second. I have to include it this way. I have to write it as a formula when I write it. Hold on one moment, folks. It's taking me a second to type this out. There we go. Okay, so you've got 2 different ways that you can write these hypotheses. Again, I'm going to recommend that you write the hypotheses this first way, where you have an actual number associated with your hypothesis. Okay, because that's a little bit more like similar to what you're used to doing with one proportion tests, where you have an actual number that you're plugging in as your parameter, right? So in each of these cases, 0 is the parameter, if that makes sense. Like the actual value for the parameter, right? It's the same with this, like the second way that you can write these. It's just you don't have a number, right? Okay, so shocker, again, we have the same 3 conditions: randomness, 10%, and success fail. Okay, now standard deviation is where this changes a little bit. Okay, and here's why. When you did one proportion Z tests, right, you would always have a claim that you were attempting to disprove, right? A parameter would be given to you in the problem, okay? When you're talking about 2 proportion Z tests, which is what we're doing here, often the problem will not give you 2 true parameter values. Rather, they will give you sample values and say, do these samples provide sufficient evidence that this population is greater than this population, or that this population is not equal to this population, right? So that complicates our standard deviation formula a little bit, right? So because we're dealing with 2 different parameters, our test statistic and our standard deviation has to involve both of them, okay? Standard deviation has to involve both parameters, right? So when we run a 2 proportion Z test, we're assuming that the 2 population values are equal, right? We call their common value just P without a subscript, okay? But like I said, the problem is often not going to give you the parameter values. Rather, they're going to give you sample values. So we need a way to estimate that true value for each of those proportions, right? So in order to do that, we have to combine data from both of the samples, right? And use that in our standard deviation calculation. So that combined sample proportion is called a pooled sample proportion, or you may see it called the combined sample proportion. Okay, so the way that you calculate a pooled proportion is you add the number of successes in both populations, okay, and you divide that by the total in both populations. Okay, 1 second. Let me do my little line right here. Okay, so the way that you figure that out, the total number of successes in both populations is where you add the number of successes. Okay, and then for the total in both populations, you add your sample sizes. Okay, and we are going to use this pooled proportion, which by the way is typically noted with P sub C. So it's this. It stands for the combined proportion. Okay, that's typically the way that it's notated, right? Okay, and again, the reason we're doing this is because we are not going to be given the population value. So we have to do our best to estimate what it is so that we have something to use in our test statistic. Okay, if you are not given counts, meaning if you're not given the number of successes in the problem, then the best way to find them, which we've done in previous problems, is to multiply the probability by the sample size, right? We're just talking about number of successes, which is one of our conditions that we have to check, right? So even if they don't give you the number of successes, you can easily calculate it when you do this success-fail condition, okay? So for your test statistic, okay, there's a really complex formula that you see on the left side of the screen, and I'm going to write it for you again on the right side of the screen, but the general format, okay, for the test statistic is exactly the same, okay? It's your statistic value minus the parameter value divided by the standard deviation, okay? Okay, so specifically for Z, okay, the statistic, and I'm actually going to write it over here so that I don't run out of space. So my statistic is p hat 1 minus p hat 2, right? Because my parameter is p1 minus p2, okay, minus 0, right? So we're assuming that's our parameter value, and that's why I like to have you all write the hypotheses using this first method, the alternative hypotheses using this method, so that you remember that your parameter value is 0, okay? And then we're dividing by this crazy long formula for standard deviation. But again, it should look very similar to you, okay? Like to things that you've seen before. Okay, where you have some proportion multiplied by 1 minus that proportion divided by a sample size, right? And because we're dealing with two populations here, that's going to show up twice, right? Once for each population, okay? Now here, remember, because we aren't given a true value for either population, we have to use our pooled proportion when calculating the standard deviation. And it'll be the same for both populations because we've included both populations when we calculated it, okay? So just as a little like reminder here, your statistic is this, okay? Your parameter is 0, okay? And then your standard deviation is this whole crazy long formula right here, okay? But very similar to the formula that we used for confidence intervals for difference of proportions and for sampling distributions. It's just long, okay? Other than that, other than the changes in the hypotheses, right, in the way that we write the hypotheses and in the pooled and having to calculate the pooled proportion, everything else is exactly the same as what you did with the one proportion test. So we're still going to follow our 8 steps, our acronym, the PHANTOMS, PHANTOMS, okay? Where you start with the parameter, write your hypotheses, check the assumptions for each population, name the test, calculate the test statistic using this very fanciful formula right here, find your p-value, because once you have your test statistic, right, you're going to do everything else exactly the same. Find your p-value using either the z-table or using normal CDF, right, using your technology. Remember that if your test is two-tailed, meaning that if your alternative hypothesis has a not equal to symbol in it, remember whatever you get from the z-table or from normal CDF, take that probability and multiply it by 2, only if you are dealing with a not equal to sign in your alternative hypothesis, right? So that's your O step, obtain the p-value, make a decision to reject or fail to reject the null, and then we're going to state our conclusion in context, okay? Everything else is the same. The only differences are these, your hypotheses, because they're going to have two proportions in them, and having to calculate this pooled proportion for your standard deviation. All right, so let's go ahead and try one. Okay, so in this problem, we're talking about, we're comparing proportions of children who come to school without eating breakfast in two different schools. Okay, so we have a simple random sample from school 1, and we have a simple random sample from school 2. Okay, they told us that more than 1,500 students attend each school, and so the question is, do these data give convincing evidence at the 0.05 significance level of a difference in the population proportions? Okay. All right. So we're going to pick out a couple of things that are important here. First, we have at the first school, we have 80 students and 19 of them had not eaten breakfast. At school number 2, we have 150 students in our sample. 26 had not eaten breakfast. Okay, and then our significance level, they gave it to us, so that's our alpha. And that's our cutoff level is 0.05. Okay, and then the last thing I want to point out is they are asking us about a difference in the population proportions. So not whether school 1 is larger than school 2 or less than school 2, just that they're different. Okay, so what that tells me is that my alternative hypothesis is going to be a not equal to hypothesis. All right, so let's go through all of the steps. So P is the parameter. So the parameter that our test will examine here is we are estimating the difference in the true proportion of children who come to school without eating breakfast in school 1, which I'm going to call P1, and school 2, which I'm going to call P2. I know my spacing is a little off here. Let's go like that. Just it's a little easier to read. Okay, all right, next, hypotheses. And I'm actually going to write these out rather than drawing them. Okay, so my null hypothesis is that P1 minus P2 equals 0. Okay, and then my alternative hypothesis is that P1 minus P2 is not equal to 0. Okay. All right, so next, assumptions. So we're first got to check for random sample, and they did say that we have a simple random sample in both of our schools. Okay, I'm trying to pull all of it forward for you here on the left-hand side. Okay, so we can just say we had a simple random sample stated for both schools. Okay, then we have the 10% condition next. Okay, so for school 1, okay, I'm going to do 10 times the sample size, which was 80, equals 800, and that's less than the total number of kids at school 1. Okay, and then for school 2, I'm doing 10 times, again, my sample size, which is 150, which is 1,500, which is, I know we're right on the cusp, but they do say that more than 1,500 students attend each school. So 1,500 is less than the total number of kids at school 2. Okay. All right. Okay, then I have to check is my sample large enough, right? So for school 1, right, I'm doing NP is, and that's, remember, number of successes, which they told us actually in the problem was 19. Okay, and that's greater than 10. And then my number of failures, which is n times 1 minus p. And I really should be using my subscripts like n1, p1, n1, p1. But I'm not, just for sake of time here and ease. Okay, so if my number of successes here was 19 and my sample size is 80, then that means my number of failures is 61, which is greater than 10. Okay, and then I have to check again for school 2. So same thing, NP, my number of successes was 26. Right? They told us that in the problem, greater than 10. Okay, and then number of failures, N1 minus P. If there's 150 students in this sample and 26 successes, that means there's 124 failures, which is obviously greater than 10. Okay, so the key thing to remember for difference of proportions is that you have to check your assumptions for each population. Okay, all right, so N is the next step, okay, which is to name the test. Okay, so I know I wrote it as a 2-sample z-test on the left-hand side, but the most accurate name for this test is a 2-proportion z-test. You could say 2-sample z-test. They mean essentially the same thing. Okay, and then we also have to set our alpha value at this level, and they told us what that was. They told us that my significance level was 0.05. All right. Okay, next, we have to calculate our test statistic. Okay, so we need a couple of things. Okay, we need the sample proportion for each school. Okay, so that's p hat 1 is 19 out of 80. You usually want to convert that to a decimal. Okay, so that's 0.2375. Okay, and then I do the same thing for school 2. So p hat 2 is 26 over 150. Right, and when I do that math, I get 0.1733. Okay, so my statistic is p hat 1 minus p hat 2. Right, so I'm literally just going to subtract those two, and I get 0.0642. Okay, so just like the confidence intervals, I'm going to put a little box around this number because I'm going to need it in my actual test statistic. Okay. Okay, then next, we have to calculate our pooled population proportion, or we have to calculate our pooled proportion. Okay, so I'm going to add the number of successes in each school, okay, which was 19 plus 26, right? We have to combine our samples into one pooled proportion so that we can calculate our standard deviation, okay? So 19 and 26 are the number of successes in each, okay? And then my sample size in each of these is 80 plus 150. And then I'm just going to plug that into my calculator. So I get 0.1957, okay? And we're going to use that in our standard deviation calculation, which comes next. Okay, so this guy right here goes into our standard deviation calculation. Okay, so you have the same thing in the numerator of both of these fractions. Okay, which you can see it written out on the left-hand side, and I'm going to write it out for you here on the right-hand side. So I have my pooled proportion, 0.1957, times 1 minus that, which is 0.8043, Okay, so I'm going to have the same thing in the numerator for both of my fractions that are inside the standard deviation. Okay, but for this one, because it's school number 1, the number on the bottom is 80 because that's the sample size. Okay, and then I'm going to do the same thing. So 0.1957, 0.8043 divided by, but this is school 2, and the sample size for school 2 is 150. Okay, so I'm just going to plug all of that into my calculator, and when I do, I get that the standard deviation is 0.0549. Okay, so this is another thing that I need to calculate my test statistic. Okay, and I know I didn't leave you all a ton of room here. Apologies there. Didn't leave myself much room really either. Okay, but now I have the information that I need to calculate my z-score. Okay. So remember, it goes your statistic, which is in this purple box right here. So z equals 0.0642 minus, and then it's minus 0. Your parameter is 0. Okay. Divided by 0.0549. So that's the other thing that's boxed in purple right here. Okay. And then that number is 1.17. Okay, so that is my test statistic. That's what I'm going to use to obtain my p-value. Okay, so we're going to move on to one of the last steps, okay, which is to obtain our p-value. Okay, so what we are finding here, what we are calculating is the probability that p hat 1 minus p hat 2 is not equal to this statistic that I got, the one that's boxed in purple up here, 0.0642. Okay. Which is the same as saying the probability that z is not equal to 1.17. Okay, much easier to write, that second one. Remember, you don't have to write both of these. One of them is fine, right? I just write both so you all can see the thought process, right? Now remember, because this is a not equal to probability, right? Usually what I tell you all to do is, and what the rule is you have to do 2 times the probability, and then usually what I have y'all do is if z is not already negative, switch it to a negative and do this. Have it the probability that z is less than the negative version of your test statistic, okay? Because the negative version of your test statistic is easier, and the less than probability is easier to find than your than a greater than probability when you're using a z-table, right? So this is 2 times, and then that probability from, I think I got it from my calculator. So this probability is 0.1210. So 2 times that is 0.2420. Okay. So obviously my p-value is 0.2420, which is definitely greater than alpha. Okay, so I'm going to fail to reject the null. Okay. Right. And then my very last step here is to state my conclusion in context. Okay. Which that's another spot where you want to use your script. Okay. So my script is because the p-value is, and it's greater than, in this case, is greater than alpha, we fail to reject the null. Okay, we don't have enough evidence to support HA. And then you have to say what HA states, right? Which states that the difference in the true proportion of students who didn't eat breakfast at the two schools is different. Okay, so again, I'm mostly just restating what I said in the parameter step right here. Okay, all right. So with that, I know that's a lot. It's a really long process, especially because you have this extra pooled, proportion that you have to find. So it takes a little bit longer to like calculate the standard deviation. But what I'm hoping you're seeing is that after you do like the hypotheses that are different and having to check the assumptions twice, that the mechanics of this are the same as the one proportion test that you did a couple sections ago. All right. So we've got one more here, okay, about our teenagers going deaf. Okay. So I want you all to try this one on your own, right? It's still a two proportion z-test, right? So I want you to try this one on your own. But I do want to note for you that the question is, do these data give convincing evidence that the proportion with hearing loss has increased? Okay, so what that indicates to me is this is going to be a greater than probability in your alternative hypothesis. All right, so give this one a try. Pause the video, give this one a try, and then check back with me to see how you did. All right, folks, so go ahead and check your answers against mine. So in this problem, we are estimating the difference in true proportion of teen hearing loss from 1998 to 2005. I labeled 98 as P1 and 2005 as P2. So we're trying to figure out if hearing loss has increased. So the way that I wrote my hypotheses was P2 minus P1 equals 0, and then P2 minus P1 is greater than 0, right? You put the later year first, right, to see if it's increased, right? And you have a greater than symbol there. So we're trying to see if this is if this true value is greater than 0. That would indicate that we have an increase in hearing loss over time. Okay, I went through and checked my assumptions. So I did have a simple random sample stated in the problem for both years. Okay, for 1998 and 2005, I definitely met the 10% condition. Remember, the sample size for 98 was 3,000, and the sample size for 2005 is 1,800. So that means you have to make sure you check each one because you're going to get a different number, right, for each of those. Okay, and then for my large enough sample, that also works, which you would expect it to because these samples are very large, right? Like 3,000 people, 1,800 people, that's a lot, right? You're definitely guaranteed, unless the probability of the sample proportion is really, 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 really small, you're essentially guaranteed that this assumption is going to work out. But you have to check it nonetheless. So my number of successes for 88, I realized I wrote 1998 in a couple of places. Whoops, I meant 1988. Sorry about that. So in 88, my number of successes was 450. In 2005, number of successes was 351, right? So obviously both number of successes and number of failures are both greater than 1 in both of these years, okay? This is a two proportion z-test. You could have also called it a two sample z-test. And then I also need to set my alpha value. They did not give us one in this problem, so a safe bet is 0.05, okay? So for my test statistic, this time they gave me, I didn't have to calculate each of my sample proportions because they gave me what they were exactly. So in 88, my sample proportion was 0.15. In 2005, it was 0.195. I wrote my sample sizes out there as well. So my statistic here is p hat 2 minus p hat 1, right? So 0.195 minus 0.15, and I got 0.045 for that. Okay, and then in order to calculate my standard deviation, I have to calculate my pooled proportion. So that's the number of successes in each year, which again, I pulled directly from this step right here. Okay, you've already done the work. Don't try to calculate it again, right? So you add the number of successes. That's your numerator. Add the sample sizes. That's the denominator. Divide those in your calculator. So when I did, I got 0.1669 for my pooled proportion. I plugged that information into my standard deviation formula and got 0.0111 for my standard deviation. So my test statistic is 0.045 minus 0, right? Remember, that's your parameter, right? Because that's what shows up here, right? That's your parameter, okay? And then divided by 0.0111, and I got that my z-score, my test statistic, is 4.05, okay? So for p-value, we're finding the probability that the difference in those samples is greater than 0.045, because remember, my alternative hypothesis had a greater than symbol in it, okay? So that's the same as saying what's the probability that z is greater than 4.05, okay? I wrote the complement version just for my people that like to use the z table. So remember, a greater than probability for z is the same as 1 minus the less than probability for that same number, okay? And you'll notice that that value, 4.05, is not even on the z table. So because it's too large, it's too extreme. So if that's the case, then we would just say that that probability is essentially 1, because that z value is too extreme to be on the z table. So my p-value here is 0, right? Since my p-value is 0, that's less than any alpha value I could set. So I'm going to reject my null. Okay? And then the last thing is I have to state my conclusion in context. So because my p-value is less than alpha, we reject the null. There is evidence to support HA, the alternative hypothesis, which states that the difference in the true proportion of teen hearing loss between 1988 and 2005 is greater than 0, right? So i.e., I forgot to close my parentheses here, i.e., my hearing loss over time, or these teens' hearing loss over time, has increased. Okay? And then I put one additional question on there that I wanted you all to think about. And so I hope that you got the same answer as me. So this additional question, which is a common type of question they like to ask on like an investigative task, because it combines what you learned in studies and experiments in Unit 1 with this actual inference process of hypothesis tests. So the question is, between the two studies, Apple introduced the iPod. If the results of the test are statistically significant, which they are, okay, because we rejected the null, okay, the question is, can we blame iPods for the increased hearing loss? And the answer here is no, we can't, okay, because this hypothesis test can only tell us whether or not hearing loss has increased and not what actually caused the hearing loss. The reason we can't tell what caused the hearing loss is because this, if you go back up to the problem, was an observational study, not an experiment, okay? We can only assign cause and effect relationships when we're dealing with an actual experiment, not an observational study, all right? So that is it for this video, y'all, and I will see you in the next one, in the next unit, when we're talking about inference for means. Bye, everybody.